Okay, welcome to the first video lesson for 2016, and this course is U11 higher level IB course. So our first topic is looking at patterns and sequences, and we started off in class the other day looking at different types of sequences and then identifying really that there are two that we're going to really look at in some sort of detail, and that is the arithmetic sequence and the geometric sequence. The arithmetic sequence, just to clarify, as we roll through this video, and I'm making notes and talking. If you can be taking notes, some of this stuff you'll already have. I'm just doing a quick recap, and then as we move forward, please take the notes down, pause the video as necessary. Even sometimes do an example before I've done it, so that you can check your work on it. But it's just a quick recap so far. We've looked at arithmetic sequences, and a feature here of arithmetics are that they have a common difference. So we can see a common difference, either positive or negative, and with geometrics we can see a common ratio, which we're calling R. We also got as far with arithmetics to identify that nth term, and so we got to the point where if we're going to concentrate on arithmetic sequences, for a moment, then what we established was that the nth term of an arithmetic sequence, un, was equal to the first term plus 1 less than n times the common difference. So we looked at some examples of that, and we're working through exercise 1b, which is, I think, that sort of work. So that's the nth term of an arithmetic sequence. So we'll look at, we're calling this the nth term of an arithmetic sequence. What we're going to look at now is how to evaluate the sum of an arithmetic sequence. I'm just going to go through one or two things here with you, and then we'll get some notes. So that now we're going to look at the sum to n terms. Now, just to explain what the difference between sequences and series. A sequence is the string of numbers separated by commas or whatever, 1, 3, 5, 7. The series is the sum of the sequence. So if we're going to take a sequence and sum them, that's called a series. Just so that we understand what the language is all about. So now let's start to look at series. So let's have a look at the sum of an arithmetic, sorry, my writing's terrible, arithmetic sequence, which we're going to call a series. Okay, so the sum of an arithmetic sequence, so that's Sn. Sn equals, so this is what we're going to try and establish. Okay, so what I want to do before we get into that is just have a look at, if we look at a simple example, say 1, 3, 5, 7. So this is our sequence. As soon as we change these commas to pluses, now we're looking at a series. So 1 plus 3 plus 5 plus 7 plus 9 plus 11. Let's say we're going all the way up here to, well, now let's just leave it at that actually. Let's just leave it at that series there. Well, that's an arithmetic. As you can see, the common difference here is 2 as we go up. And we could just add them up because it's not that hard. 4, 9, 16, 25, 36. We know that sum is 36. Don't really need a formula. But just humour me for a minute and let's try and work one out. And in fact, there's a great story about this this genius Gauss, this young fella Gauss. I don't know, was he Greek? We're talking 500 BC or something like that. Sorry, my history is not brilliant. But he shocked his primary school teacher when he was asked to add up the numbers from 1 to 100. He did it in a couple of seconds as an 8-year-old or something. Quite a clever little chap. But this is how he did it, and that's a great story, and perhaps it did inspire some work in this field. But it doesn't really matter because it's just a nice little story. But how he did it was he. All right, look at his challenge. His challenge was 1 to 100, and we'll come back to this one in a second. Actually, no, we won't. We'll do this now, and we'll go to the Gauss problem in a moment. So what we could do is we recognise, let's just have a look at the sum of the first and the last term, which hopefully you recognise there as 12, and then look at the sum of the second term and the second last term. and the third term and the third last term. These sums are all the same. Now, that makes sense, doesn't it, really, when you think about it, because 1 and 11, which is 12. Now I'm starting with 3, which is 2 more than 1, but the second last term is 2 less than 11. So this is 2 more than 1, but this is 2 less than 11. So it makes sense that each time we go up, we're going down by the same amount on the other end, so they all sum to 12. So this is a great little pattern, isn't it? And all we need to do is work out, well, we've got 6 terms, so there's 3 pairs of 12. So all I need to do here is work out how many pairs I've got, multiply by one of those pairs, because they're all going to be the same, 3 12s of 36. So what you can imagine what Gauss did was actually he did this in his head because he was a bit of a child genius, but he was asked, and I think he was in trouble, and the teacher was trying to occupy him. He 1, 2, 3, 4, 5, and he had to add up the numbers from 1 to 100. So 95, 96, 97, 98, 99, 100, right? And so this is his thing. So what he did, quickly thought, maybe he thought of it before, while he was thinking about it at some point, contemplating numbers, as obviously he liked to do. He took the first 2 numbers and saw that they were 101, and he took the second last, and realised that actually what we were dealing with was just a whole bunch of 101s. How many 101s? Well, there were 50 101s, and he was good enough in his head to calculate 50 times 101, which is 50,050, I believe. In fact, of course, that's not correct, is it? It's got they can get rid of that 0 there. It's only 5,050. So that's the sum of an arithmetic. Nice little pattern, isn't it? So if we can work out the pairs, then we just find out how many pairs we've got. So what that lends itself to is a formula that says, right, so U1, so the number of terms. So if we've got 6 terms, it's going to be 3 pairs, isn't it? So we're going to halve the number of terms, n over 2. Over here, the 50 represented half of the 100 terms. The 3 represents half of the 6 terms. So n over 2. Now we multiply that by the first term, this one here, plus the last term. Now the last term is this here, isn't it? The last term is the nth term, because we're looking at the sum of n terms. So the last term is actually u1 plus n minus 1d. So we can simplify that to n over 2. We've got 2 u1s here, so twice the first term plus n minus 1d. Brilliant. Let's check that on our 1 to 100 scale. So for the example of 1 plus 2 plus 3 plus all the way to 100, our sum of 100 terms will be equal to, let's work this through, 100 over 2, which is 50. So we halve the number of terms. We take the first, we double the first term, so that's 2 plus n minus 1, so 99 times the difference, which is 1. So we get 50 by 2 plus 99, which is 101, which we've worked out to be 5,050. Okay, so there's our sum to n terms. Really nice little feature, that one. Okay, we're ready to have a look at geometrics then. What I might do is I might close that there. And this is work to do with exercise 1C. So I'm going to close it there because I've made 8 minutes and that's probably enough for one video. Exercise 1C is something that we'll tackle when we next meet in class. In fact, that's going to be later on this afternoon. And I'll make another YouTube lesson on geometrics and finding the nth term of a geometric, and then also finding the sum of n terms of a geometric. So I'll close there and I'll see you soon.